Welcome to ME 227 Thermodynamics I. This is an introductory thermodynamics course as taught at the Department of Mechanical Engineering at the University of Saskatchewan. This first video is just going to be a general introduction to the topic of thermodynamics. So we'll start off with a definition of thermodynamics, and this is actually not all that easy to find. There's lots of different aspects of the science of thermodynamics, and we're just going to focus on the ones that are relevant to this introductory course. So first of all, thermodynamics is the study of energy and the relationships among the properties of matter. So it sort of appears like there's two different topics in that definition, and to some extent that's true, but there's a real strong connection between these two parts of this definition that hopefully we can illustrate in this introductory video. So the most important word in this definition is energy. Think of thermodynamics as a study of energy, and more specifically, as we'll see, it's energy transformations. How do we transform energy from one form to another? And in particular, how efficiently can we transfer energy from one form to the other? So we'll be talking about energy a lot in this course. Historically, thermodynamics is really the study of how heat can be used to produce work. So by historically here, I'm talking in the context of the dawn of the Industrial Revolution. So back in 1774, according to the date on this picture, James Watt invented the first steam engine. Well, there's some debate over whether he actually invented it or whether someone else did and what the exact timing was, but the general attribution is to James Watt. And so this is one of the very first times in human history that heat was used to produce work. Many thousands of years earlier, humans harnessed fire, and they used heat for a long time to keep warm and to cook food. However, to produce work, to create a moving mass or turn a rotating shaft using heat, and that's generally attributed as the key development that allowed the Industrial Revolution to happen. So let's look now at a few more detailed points about thermodynamics. First of all, we're going to be asking, how is heat converted into work? A very important topic. Also, how efficiently can heat be converted into work? How are the properties of matter related to each other? So we'll see as we go forward here, by properties we mean pressure, temperature, and energy, those sorts of things. So there's a definite connection between these different aspects of thermodynamics. So first of all, I want to introduce this whole topic just by looking at some examples of thermodynamic systems. So this hopefully will illustrate and bring forward the things that we've talked about so far: the concept of energy, concept of converting energy from one form to the other, and how the properties of matter might be of concern when we're figuring out how those energy transformations occur. So, examples of thermodynamic systems. First one I want to talk about is thermal power generation. So this is the basic cycle that's happening in many thermal power plants around the world, regardless of what the source of the heat is. Historically, of course, it was coal, but it could be natural gas, it could be thermal solar, it could be nuclear. Any source of heat that we want to convert into a rotating shaft, which is then, of course, used to generate electricity. So let's take a look at a power generation cycle, and later on in the course we'll be calling this particular cycle a Rankine cycle, but the name isn't too important right now. So what we do is we start off with some water. So down here we have just ordinary water, and we'll be putting some properties on here in a moment to give that a little bit more detail. But we're just starting off with water, and it's going to be essentially at room temperature, as we'll see later. We put it through a pump. So the sole purpose of that pump is to pressurize the water. So that's the first step: pressurize the water. Then we take that water and we put it through a steam generator. So this is where the external source of heat comes in. There's heat added to this from some external source. After it goes through the steam generator, it enters a turbine where work is extracted. So the hot pressurized steam is used to turn a turbine, which in turn turns a rotating shaft and delivers work to the surroundings. And of course that will be used to generate electricity. And finally, after the steam exits the turbine, it enters into a condenser where heat is removed and it's returned back to a liquid ready to go around the cycle again. So that's the four basic components of a Rankine cycle. So the main thing we want to look at here next is the energy transfers with the surroundings. So the reason this is called a cycle is because this fluid is just going around and around in circles, or it's going through a cycle, or more specifically, a thermodynamic cycle. So the main energy exchanges with the surroundings occur in these four basic components. So the first of those is there's work into this cycle. So we have to have an electric motor of some kind out here that is doing work on our fluid in this pump. So work into the cycle at that point. Next, the pressurized water goes through the steam generator where heat is added. So we have another energy transfer with the surroundings, and that is heat being added from the outside into the water in the steam generator. After that, the hot pressurized steam goes through the turbine, and then we have work out. So this work out, of course, is very large. This is the main purpose this thing exists, is to produce this work, which then can run an electric generator and produce electricity. And then finally, we have heat rejected in the condenser. So there's four basic energy transfers with the surroundings. Two of them involve work transfers, work done on the fluid here and work done by the fluid here on the surroundings. And two of them are heat transfers, heat added here in the steam generator and heat rejected in the condenser. So remember, this condenser is taking low pressure steam here after it's gone through the turbine, and it's converting it into liquid. So a bunch of heat has to be removed to do that. So those are the four basic energy transfers with the surroundings. And you'll notice two of them involve heat transfer and two of them involve work transfer. And the distinction between heat and work is a central topic in this class. We're going to be talking lots about that. They are definitely not the same thing, and we really need to make a distinction. But the basic thing that this power generation cycle is doing is converting heat into work. In terms of magnitude, this is very large and this is very large. So a large part of the heat being added here is being produced as work. However, there is also a significant amount of heat rejected here, and in this particular cycle, a relatively small amount of work added. So the magnitudes of these four things are also very important, and that determines the efficiency of this cycle. Of course, ideally, we would like all of the energy added here as heat to be produced here as work, but we'll see by the time the course is done that that's not possible. But we're certainly interested in how much of that heat can be turned into work. So that's talking about the energy transfers with the surroundings. Now the other thing we want to talk about is the properties of the water. Turns out the working fluid in this power generation cycle is water 99% of the time. So we want to look at how do the properties of the water change as it goes around this cycle. I've just used some loose terms so far like liquid and steam, but we want to give some numbers to that. And this is where that second half of the definition comes in. The relationship between energy transfers, that's what we've looked at so far, and the properties of matter. Well, starting back at the beginning here again, the water coming into the pump is liquid, first of all, and it typically would be at about 20 degrees C, so that's sort of normal room temperature, but at quite a low pressure. Notice here I'm saying 10 kilopascals. Well, atmospheric pressure is approximately 100 kilopascals. So the pressure here in a typical power generation cycle is actually quite low. The condensers are kept at quite low pressures, and it turns out the lower we can keep that pressure, the better, but we'll look into that in more detail later in the course. So typical properties here, 20 degrees C, 10 kilopascals, and the phase it's in is liquid. Now remember, I said the purpose of the pump is to pressurize this water, and so that's what happens. We go through the pump, and at the pump exit, typical properties would be still 20 degrees C. Now we'll look at some detailed calculations later on, and this temperature does go up a tiny little bit, but very, very little. Much higher pressure now, 10 megapascals instead of 10 kilopascals, so a factor of 1,000 increase in the pressure, and it's certainly still a liquid. So this work transfer has gone into increasing the pressure of this particular working substance, the water. It hasn't increased the temperature very much, but it's increased the pressure a lot. So you can start to see how we might be concerned with the relationship between an energy transfer and a change in properties that results from that energy transfer. So that's the link between the energy transformations or energy transfers and changes in properties of substances. Now we'll continue around here. We next go through the steam generator, and notice that the pressure coming in and the pressure going out of the steam generator is the same. And to a first approximation, that's a very good assumption. This heat exchanger, this steam generator, is a constant pressure process. However, notice the temperature, of course, has gone way up from 20 degrees C up to typically 300 degrees C. And, of course, now it's changed phase as well. Now it's steam rather than liquid. So that's another thing you'll notice very soon in the course, is that we're going to be looking at phase changes of these working fluids as well. It's a very important aspect of this. So now we've gone through the steam generator. We have hot pressurized steam, high pressure and high temperature. Now we go through the turbine. And of course, a bunch of the energy stored in this steam is now going to be released, or is going to be extracted in the form of work output from this turbine. So we come down here to low pressure again, 10 kilopascals. Notice it's the same as this because the pressure change through the condenser is very, very small. Temperature is back down to 20 degrees C, so a very large temperature drop across here. But typically this is still steam. Now, in reality, it's probably a mixture of liquid and steam, but for our purposes here, this very basic cycle will say that it's still steam. So the very last process we have here is the condenser, and of course, that is a constant pressure process, 10 kPa to 10 kPa. And notice that the temperature doesn't change either, 20 degrees C in, 20 degrees C out. However, in the condenser, it's converted from steam to liquid. So there's quite a bit of energy has to be removed in order to do that. So this is a typical power generation cycle, and hopefully it illustrates the connection between those two parts of the definition of thermodynamics I gave. The study of energy transformations, so heat and work transfers like these, and the connection of those with changes in properties. So that's the changes in the properties of this water that results when we add or remove heat, or when we add or So this is just a picture of the Queen Elizabeth Power Station, which is on the South Saskatchewan River, just upstream of the city of Saskatoon, and of course that thermal power plant, that thermal cycle that we just looked at is what's happening in the Queen Elizabeth Power Station. Now actually there's quite a bit more happening in the QE Power Station. It's actually a combined cycle now. So there is a Rankine cycle that we just looked at, but there are also gas turbines in the Queen Elizabeth Power Station. So it's a combined cycle plant now. We'll look at the gas turbines later on in the course, but one of the main workhorses in this power plant is the Rankine cycle. We want to look at another thermodynamic cycle that has many similarities with the one that we just looked at. Going to change a couple of things though. The working fluid in this particular cycle, rather than being water, is going to be air. That will be the first change. Now we're going to go through many of the same processes, but not quite all the same. The first one, however, is going to be the same. So we're going to take some air here at the inlet to this thing, and this air is just going to be standard conditions. So 20 degrees C and 1 atmosphere essentially. So normal air. Now we take it and we want to pressurize that air. Now when we pressurize liquid water, we called it a pump because that's the device that would typically be used to do that. But when we pressurize a gas like air, that device is called a compressor. So this particular device is doing exactly the same thing as the pump, only because our working fluid is air rather than water, we call it a compressor. And of course it would be designed quite differently, and we have a different schematic symbol for it, but they're both doing the same thing. They're pressurizing the so-called working fluid. So that's fine. So we pressurize the air. Next thing we do is we add heat to it. Now in the last cycle this was called a steam generator, but of course we're not generating steam now, we're just heating up the air further, and so that's called a heat exchanger. So there's some external source of heat supplying heat to this thing. So after we have hot pressurized air here now, we put it through a turbine, just exactly the same way as we did for the Rankine cycle, for the power generation cycle that we just looked at. Now here's where it gets a little bit different. This turbine is producing work, so that's the same as in the Rankine cycle. However, now we can see what this work is being used for. Work isn't being delivered to the surroundings. This work is being used to run the compressor. So the hot pressurized gases here go through the turbine, produce some work, which in turn runs the compressor that happened early on in the cycle. So that's one of the big differences between this particular cycle and the one that we just looked at. That and the fact that air is the working fluid instead of water. So let's just take a look at the energy transfers with the surroundings that have happened so far. So we've got air coming in here. First thing that happens is work is done on the air in the compressor. Next thing is heat is added to the air in the heat exchanger. So those two work transfers are very similar to the Rankine cycle. Next thing that happens is work is coming out of the working fluid. And of course, as I said, that work is actually being used to run the compressor. So the magnitude of these two works is the same. Now the next thing that happens in this particular cycle, so now we'll look at some typical properties, just like we did in the Rankine cycle. So this is air, remember, so we have 100 kPa, 20 degrees C, basically atmospheric conditions. When we pressurize a gas, both the pressure and the temperature go up. Notice when we pressurized the water in the last cycle, the temperature basically didn't change and the pressure went up. But when you pressurize a gas, both the pressure and the temperature go up. Assuming a couple of other things, but we'll get into that in detail later in the course. So 100 kPa and 20 degrees C, pressurized up to 1 megapascal and 300 degrees C. So the pressure increases by a factor of 10 and the temperature goes from 20 up to 300 degrees C. So we have hot pressurized air here. We go through the heat exchanger, and the heat exchanger is a constant pressure device, so the pressure doesn't change, but the temperature goes way up to typically 1200 degrees C. So very hot pressurized air here goes through the turbine, and now this turbine only needs to extract enough energy to run the compressor. So typically, coming out of the turbine, we would still be at quite a high pressure, 450 kPa, and the temperature will drop down somewhat to 900 degrees C. So notice there's still a lot of energy left in this air. Very high pressure, 450 kPa, and very high temperature, 900 degrees C. So this is where this cycle gets a little bit different than the last one. The last component in this cycle is a nozzle, and we didn't see a nozzle in the Rankine cycle. So a nozzle is something that takes hot pressurized gases and increases the velocity. So there's lots of energy stored in here, but it's internal energy because it's there as a result of being at a high temperature. But the kinetic energy of this fluid is actually quite low. So a nozzle converts that internal energy into kinetic energy, so that when it comes out the end here, it's at 100 kPa, so that's back to atmospheric pressure finally. Still quite warm actually, 760 degrees C, but it's traveling at about 500 meters per second, whereas coming in, the velocity would be negligible. So it's converted some of that internal energy into kinetic energy. So at the inlet of this thing, we have a very low kinetic energy, and at the exit, we have very high kinetic energy. So the entire purpose of this device is to use some source of heat to convert the air from low kinetic energy to high kinetic energy, because that's the net effect of this thing. The work transfers here are all internal to this cycle. It does produce some work, but that's used to run the compressor internal to the cycle. The air is coming in with low kinetic energy, a lot of heat is added, and it's leaving with a high kinetic energy. Now notice it's leaving with quite a bit higher temperature than it came in with as well. If we compare these temperatures, it's coming out at 760 going in at 20. So certainly some of the heat that we added here is just warming up the air, but a significant part of it is going into increasing the kinetic energy of the air. So this device is a jet engine. And if we take 4 of these things and strap them onto an apartment building, we get a jumbo jet. So that's the cycle we've been looking at, is what's happening inside of each of these jet engines. So they're taking relatively slow moving gases coming in the front and turning them into a very, very high velocity jet of gas coming out the back, and that of course produces thrust, which is what makes the airplane fly. I want to look at a small variation on a jet engine, and this is called a gas turbine. So again, everything that I've got here is the same. The only difference between this picture and the one that we were looking at for a jet engine, there's actually 2 differences. First one is, notice there is no nozzle here. So we don't have a nozzle accelerating the hot gases up to a high kinetic energy. And the other thing that we notice, it's a little bit more subtle, is that there's a work output here. So the compressor in this one and the combustion chamber or the heat exchanger are basically the same. But notice that this turbine, it produces work that runs the compressor, so that's the same, but it also produces extra work that is used in the surroundings somewhere. So very, very similar device, only a gas turbine would have a much larger turbine, and it's trying to extract as much energy as it can from these hot pressurized gases and produce as much work as it can in the turbine. A little bit of that would go back to run the compressor, but the majority of it hopefully would be available for work in the surroundings. So this would typically be used to run an electric generator and generate electricity. So when I talked about the Queen Elizabeth Power Station being a combined cycle, it has several gas turbines, and the exhaust gases from those gas turbines are used as the heat supply in the Rankine cycle to produce even more electricity. So that's called a combined cycle. I'm going to talk in quite a bit of detail about those near the end of the course, once we've figured out how to analyze all of these components individually. And this is a picture of inside of a gas turbine. So it's taken apart here. At the front end here we see the compressor blades. So the air comes in here, goes through this compressor blades. So we get pressurized air at this point. Then it actually comes out. There's a combustion chamber is usually mounted on this ring here. There's a whole series of them all the way around. So the air comes out, hot pressurized air comes out. The combustion chamber adds a bunch of heat to it. Temperature goes way up, and then it comes back in here, and these are the turbine stages you can see at the back end here. So that turbine produces work. Both the compressor and the turbine are connected to a common shaft running through the middle of this thing, so the turbine runs the compressor, but there's also a shaft coming out the back of this thing that runs an electric generator. So this is a picture of the other side of the Queen Elizabeth Power Station, and these devices here are called the heat recovery steam generators. So the exhaust gases from the gas turbine that we just saw go into this thing and eventually come out the top here, but the water from the Rankine cycle also enters this thing, and heat is transferred from the exhaust gases into the water that is supplying the Rankine cycle in these exhaust gas heat exchangers. One final thermodynamic cycle we want to look at in this introduction is refrigeration. This is another application that we'll be looking at in a fair bit of detail later on in the course. And again, it's a thermodynamic cycle because the working fluid is going around and around in a circle and experiencing, as it turns out, 4 different processes. This particular type of refrigeration system is called a vapor compression refrigeration system. It's the one that we'll be looking at in detail later on, and it's also by far the most common type of refrigeration system. So in this cycle, the working fluid is actually going around in this direction. So what's happening to it is, first of all, it goes through a compressor, so there's work done on the working fluid. Then it enters a condenser where heat is rejected out of the working fluid. and then it goes through a throttling valve. Now there's no work or heat transfer in the throttling valve, but the pressure drops way down. And then finally it enters the evaporator where heat is added to the working fluid. So if you think about this refrigeration system in a practical application, like a refrigerator in your kitchen, this evaporator is inside of the refrigerator. So you have very cold refrigerant inside the evaporator and only moderately cold contents in your refrigerator. So your refrigerator interior might be at 4 degrees C, but the temperature of the refrigerant going through the evaporator would be much cooler than that. So heat is added to the refrigerant in the evaporator. So this is the cold part of the cycle that would be inside of your refrigerator. Then it goes through the compressor. So this condenser would be on the outside of the insulated chamber that is your refrigerator. So just in your kitchen, the refrigerant going through the condenser would be very hot, and so heat would transfer from the hot refrigerant here to the relatively cool surroundings of the inside of your kitchen there. So heat is rejected in the condenser and added in the evaporator. So let's take a look at typical refrigerant properties as it goes around this cycle. Well, at the inlet of the compressor, the refrigerant would typically be at about minus 25 degrees C and perhaps 100 kPa, and it would be a vapor. So that's also inlet to the compressor, of course, is the exit of the evaporator. So this shows you that the temperature inside the evaporator is quite cold, and so the contents of the refrigerator, which are warmer than that, heat will transfer into the evaporator. After it goes through the compressor, same as the compressor at the front of the jet engine, the pressure goes up and the temperature goes up. So it is still a vapor, and the pressure is up to 700 kPa and the temperature up to 40 degrees C. Then we go through the condenser, and remember, the names of these heat exchangers are actually quite helpful. We start off with a vapor, we go through the condenser, so it comes out as a liquid because it's condensing it. Again, the pressure really doesn't change very much through a condenser, so for our purposes here we're saying that they're the same. And the temperature typically goes down to 25 degrees C in this illustration. Through a throttling valve, the main change through a throttling valve is the pressure drops. So notice in this cycle that we can divide it in half like this. Down here we have a low pressure, and up here we have a high pressure. So the compressor takes us from low to high, and the throttling valve drops the pressure down from high to low. So when we go through the throttling valve, we come out at 100 kPa, so that's our pressure in the evaporator. We're back down to the pressure in the evaporator. It's a mixture of liquid and vapor, and it's down at our cold temperature again, minus 25 degrees C. So we'll be looking at this throttling process in detail when we look at refrigeration systems, because that's kind of the key to the whole refrigeration system. It's the simplest component by far, but the throttling valve is the one where the very, very low temperature that we require in the evaporator is achieved. So we'll see how that works exactly. So during this introductory video, we've introduced just the general concepts that we're going to look at in the course, and that's transformations of energy. The two types of energy transfer that we're going to be concerned with are heat transfer and work transfer, and we've seen lots of examples of those in these three thermodynamic cycles that we've looked at. And the other big topic in thermodynamics that we're going to look at is the properties of working substances. So the ones that we've looked at here are water, air, and refrigerants, and we're going to learn when these undergo heat and work transfers, how do their properties change, and how does the type of component that they're going through affect how their properties change. So that's been our introduction. The next video we're going to be looking at just some definitions, dimensions, units, and a whole bunch of definitions in thermodynamics, just so that we get all on the same page in terms of terminology. We'll see you in the next video.